the idea that I had today is to present a way of detecting robust constraints in cosmology, and by having many data together so that we can test thoroughly our modeling. So first, what I mean by large scale structure, probably this is also something we know, but let's go to the basics. The idea is that we start with some field that is very thousand at the beginning, and then just by gravity, you start having this filamentary structure. And the idea is that we want to map this distribution in the universe and compare it with our theoretical predictions. And this is because, at least for me, what I care is about the fundamental nature of physics and not that much about how beautiful this might be. So the problem is that unless you do field level, as we were discussing on Monday, you need to do statistics. So you have your matter field on the left, you need to look at the quantity, that is basically the over densities of matter, and then you do some kind of compression, some statistical studies. In particular, I will be working on Fourier space. So basically, the power spectra, this is the covariance of your over density field on Fourier space. And as you can see on the plot on the right, if you change a little bit the amount of contact matter or your equation of states, you can see changes on the matter power spectrum, and then you can use that to infer if your model is good or not. So the problem is that we don't observe matter directly, right? Because most of the matter is in the form of a dark matter. So we need to use tracers. And the tracers I will be using in this talk mainly is the same as I was using, and everyone probably except Jose. It's basically galaxies, in particular galaxy clustering, as Mateo was explaining, at very large scales. You can see on the plot on the left that galaxies traces very well the large scale structure of the universe. But because you are only seeing the visible matter, there is a bias, the linear bias, that relates to the over density of matter and the over density of galaxies. However, if you go to much smaller scales, you need to start worrying about nonlinear galaxy bias, and things become more complicated. The good thing about galaxy clustering is that it gives information about what's the structure of the universe at a specific time. It's a local quantity. If we go to the right and see the power spectra, we see that the galaxy clustering is going to be pretty bad on constraining the growth of the structure, just because the amplitude of fluctuation is degenerated with the galaxy bias. But it's going to be good to constrain the scale dependence or matter-ness because it's local, and you cannot go to very small scales because of the galaxy bias. The second quantity, the second tracer, is going to be with lensing. In this case, we know that this deflection, this distortion on the shape of the galaxies that we observe, just because they find structures in between. Since it's affected by both visible and dark matter, it's an unbiased tracer. Since it's affected by all matter, visible or not, is an integrated effect, which means that you will lose some information, and also it's noise limited. So you need millions of galaxies to have a good signal to noise. If you look at the power spectra, it's very complementary with galaxy clustering. So it's unbiased, so you can pin down the amplitude of fluctuation. It's good to measure the growth. Since it's integrated, you lose information about the scale dependence, and you can go to much smaller scales than in galaxy clustering. Caveat here, you will have to worry about values at some point, and maybe intrinsic alignments. That some shapes of the galaxies might be aligned with the filamentary structure of the universe. But in general, you can go to much smaller scales than with galaxy clustering. So I will be talking in the context of photometric surveys. Basically, these are kids HSC and DS. We have here people from all collaborations that HSC. Yeah. So I was not part of any of these. But I will be using the public available data. Thank you very much for making it public. And then also LSST and Euclid. I'm a member of both of these, although I'm mainly working in LSST. I'm the leader of one of the conveners of the large scale structure, the Wickles in a large scale structure working group. And basically, in photometric surveys, in comparison with spectroscopic surveys, is that you are observing, they are much faster because you are observing not the spectra, you're observing basically just in broad color bands, which means that you lose information of the radial distance, the redshift of the galaxy. But it means that you can observe many more, and they also have good image quality, which means that you can do very good Wickles analysis. Since you lose information about the redshift, what you do is you have your sample of galaxies, and then you bin it in tomographic bins. So the demographic bins will be the color bands, basically. And then you basically decide what are your tomography bins, and then you put the galaxies based on the estimated redshift. Since the estimated redshift is bad, you need to cross-calibrate it with some other survey that is maybe spectroscopic or better photo sets like Cosmos. And then you find the Resi distributions that are the lines. And as you can see, the lines go beyond your edges on the tomography bin, and that is basically just because your photo set is bad, and then some of the galaxies lie outside of your tomography bin. That the overlap is in general good because that way you can do cross-correlation studies. Here I'm showing a plot that they took from Judith Pratt's paper, where she used TX5, that is the analysis pipeline for SST, and these are basically the Resi distribution taken from the science readiness document for LSTGR1. The lenses are basically the galaxy clustering sample, and sources are for weak lensing. So when you have split your sample in these tomographic bins, you project it, and then you mask bright regions, things that you have observed poorly, and assign weights as well. Mariano just gave a extended talk about how you build the mask. I will not enter into details. Then, when you have your signal map built, you start doing statistics. I will be working on angular power spectra in harmonic space. Let's assume that there are no complications here. Basically, the angular power spectra is just the covariance or the harmonic coefficients of your field. You have your map, you decompose harmonic coefficients, and then you take the covariance of those. And this is the definition of angular power spectra. And then basically the dependence kind of a power law with L, where with smaller scales are large L. And you can compare it with theoretical predictions. Basically, it's given like an integral along the path side of the 3B power spectra with two kernels that are the Qs, and they will depend on the tracer that you are correlating. In this case, in this talk, it will be basically galaxy clustering and weak lensing. You have the Resi distributions on top, the kernels on the bottom, and as you can see, the galaxy clustering, the kernels are basically following the Resi distributions, whereas in the case of weak lensing, they are smoother and smear towards zero redshift. This is caused by the integrity effect I was mentioning before. And the fact that this goes to zero here means that you are going to be much more sensitive to nonlinear scales in the matter power spectrum than in galaxy clustering. And that's also the origin of having to worry more about variable effects. So the first thing you need to do, obtain robust cosmological constraints from projected large-scale structured data, is to have robust data analysis methods. And here I'm showing something I worked with for a few years already in Oxford, is to build a very flexible pipeline, Cosmotheca, that allow us to reanalyze data from the catalog level to all the way to the cosmology. And I have split it here kind of the main steps. The first step is like we take some publicly available catalog, or we build our own, and then we follow the service prescriptions about how you account for the systematics, the mask, etc. That's very service specific, and fortunately, service have done a very good job on describing how to do that. So thank you. Second is you do the statistical analysis, and this step is widely independent from the survey details. Mainly just depend on the survey geometry, on the footprint. So we use an unbiased estimator that's called SLCL, as implemented in the master. And for the covariance, we use an accurate and fast analytical estimation that I developed in 2 different papers, the narrow kernel approximation that I think now is the standard. It has been thoroughly tested by us and by everyone that has been using it, because everyone is very suspicious about this analytical thing. So everyone has been doing it in their own laptops. And then basically the good thing is about this is that because it's analytical, it's way faster than running simulations. You can automatize the production of these covariances, and you can put tons of different motors. You have many different probes and compute the covariance between the angular power spectra and the covariances. The last bit is when you go to the inference, then you need to model the signal and the noise, and that will depend also on the tracer that you are cross-correlating. In the case of matter, you have halo bit or halo model or emulators, or you can have something different if you are cross-correlating TSZ or who knows. Then you can do the inference and find some cosmological constraints, or do some validation checks about if your residuals are actually following a Gaussian distribution or not. The second thing that you need to obtain robust constraints in cosmology is data from multiple large-scale structure probes. The idea here is that you need to test that your cosmological astrophysical model actually fits all the data that you have. And the second thing is that by combining different data, you are able to break the generalities and calibrate some of the systematics. These are very cartoonish plot with the two main tracers that I will be discussing, cosmic shear and galaxy clustering. In the case of cosmic shear, I said that basically you are mostly sensitive to the amplitude of fluctuations that I parameterize here as sigma 8, and galaxy clustering mainly to omega matter. If you combine them, you break the degeneracy with the galaxy bias, and then you can consider the cosmic growth. And you also have some systematic effects, like intrinsic alignment or the error in your residue distributions, that you can also improve a little bit when you combine them. In the case of cosmic shear, when you go to very small scales, you need to worry about variance, and then you could maybe add in the analysis some probes, as we will be discussing in this afternoon, that trace these processes, like X-rays or Suda-Seldovic, CIB. And maybe in the future, we will be even able to account for the evolution of these variant effects. So this is what we have implemented in Cosmotica so far. We have data from multiple probes. We have galaxy clustering, wave lensing, CMB lensing, CIB, TSZ, X-rays, gamma rays from multiple surveys, and we are able to combine them to produce the angular power spectra and their covariances. So if anyone wants to do some analysis with any of this, just send me an email. And also, the talk is kind of short, so that we can have many questions. So please ask.
Is there any reason why the CAB and the SC maps are ranked 2015, or just that like they haven't been updated with the last ones?
Basically that. Basically that, yeah.
Just in case, I think that like, especially in the case of the DSC, there have been many improvements in the last couple of years.
Yeah. Yeah, the time.
So about the covariance that you mentioned before, it's all based on angular power spectrum for each of these data sets, all the same.
Yeah, and the covariance I meant is the Gaussian part, so the main contributor to covariance. Then for the super sample covariance of the cognitive part, you will need to do yourself for now. Those bits, but those are kind of easy. I need to implement it, but my time is limited.
So when you combine, you assume that they're independent, the covariances are independent?
No, you account for the possible covariances. So basically, yeah, there are things that are independent because they don't overlap.
Yeah.
But apart from that, if the focus overlaps, you have the covariance basically. That's the. And then there are some technicalities like maybe at the very large scale, if you're interested on those, the approximation does not work as well, so you maybe need to run some simulation. But for the scales that normally people use in weak lensing and galaxy clustering analysis, it's fine. Yeah. So it's.
How does that scale with the increase in the number of shells that you have? Do you actually properly account for the covariance between different shells when you're doing this?
You mean like the angular power spectra?
Yeah.
Yeah. We are able to produce a covariance at the Gaussian level for all these probes and among them. So you can do analysis with all this data. Maybe not all, but 90% of the data.
How many slices can you have?
How many what?
Shells? 100, 500, or
More.
even more?
I mean, if you mean even of the multiples, more.
No. Shells and like shells in redshift.
I mean, as well as the code is there. So just if you give me a CCA computing power, we can do whatever. In Oxford, it's a bit more limited. You need to reduce the resolution to be able to do all these cross correlations.
I don't know if you're going to get later into this, but there's this thing of like pushing those smaller scales. I get that in smaller scales, also the modeling for the covariance gets more complicated. So is that also a limitation at some point that like doesn't allow you to get even in the prediction for the power spectrum scale?
Yeah, so exactly. So for some of these, in the case of weak lensing galaxy clustering, the main contribution is Gaussian, and the super sample covariance will start mattering a little bit, but for instance,
You don't have like a lot of compute for non-Gaussian clustering and so on?
not at the scales that you use because you are cutting at very large scales in there. But yeah, for instance, if you use X-rays and things like that, where probably the spectrum is more relevant, you need to do some tests. Those are things that we have. Those are this research, but you have the main component, the Gaussian part so far.
What do you use?
Maybe I said too early.
No, it's not really good. I'm wondering what you use for sampling for the inference pipeline. Is it Cobaya or?
Cobaya. We moved to Cobaya. Yeah, we were using the Python at the beginning, and we can move to Cobaya. And method calling fancy, nothing fancy. Okay, so and then this is my kind of joke talkies slide. So no, you don't read it. I will read it for you. So basically, the development of Cosmology, although it's basically something that now is almost plug and play, is very flexible and easy to implement new tracers, as I showed you. It has a lot of work behind, and it's been a development of years. So we have to develop methods like the covariances or the analytical estimation with the noise, for instance, in the piece of paper that Andy Nicola read. More recently, then because you have so many pros together, you have a huge dimensional space. We are exploring ways of making that more efficient with Borjana Hajiska and Jaime Ruiz Zapatero. Basically, we explore ways of marginalizing analytically over the news and parameters, and then you reduce the parameter space from, let's say, 40 to 6 again. Or more recently with Krishna using normalizing flows. And we have been, and this pipeline has been proved to be very useful, at least so far for us. We have used it in 16 different papers, basically doing some reconstruction of the growth or combining just the service and seeing within lambda CDM, or even in astrophysical analysis, like this reconstruction of the star formation density with CIB, that question might be interested, or like more recently studied variance. And I will focus just on these 4 papers that I were mostly involved, and then and are also quite nicely lined together. So let's go to the cosmological analysis. So the idea when we started developing this pipeline, it was to address the SA tension in a bit different way. So this plot is just for, I think probably everyone knows what SA tension here is, but this agreement between the SA that you infer assuming lambda CDM and fit CMB from Planck, or if you measure it with large scale structure. And as you can see, the most large scale structure pros prefer a lower value of SA, but the problem is that, as Anna mentioned, the modeling was very different between them, so you cannot just compare them and say, this is 3 sigma, 2 sigma, which one is the true one. So one of the things we wanted to do is to reanalyze the public available data that was at the time, and put it and do the modeling and everything at the same footprint, so that we can actually compare the results in a fair basis. The second thing is that by being able to combine it with accounting for the covariance between them, we could increase the constraining power. And the last bit is that normally people just report S8 today, but we could use the temporal information that Galaxy has to actually do a reconstruction of the growth. So we took the data that was available at that time. This is 2021, just before DSY3, just a week or something like that before DSY3 was publicly available, well, published. We took the DSY1 CR data, meta calibration, also KISS 1000, Red Magic for DSY1, the DESI legacy survey, that is this photometric survey that was locating the what DESI was going to observe later, and quasar from EVOS to get an anchor at high redshift. And we cross-correlated everything with CMB lensing. As you can see on the right, we were covering a huge fraction of the sky with surveys overlapping, so we would have to be careful about the cross-correlations. We divided the sample in 2, basically south dataset, that is basically DS, and the north dataset, that is basically KIDS and DESI legacy survey. And the division was just to address if they were, sorry. Duplicates in the sense of?
Like the name of the survey have like the same source.
No, because they are not overlapping. So basically, in this case, DS and that did that job for us. And KIDS and DESI, they are completely different. One is weak lens and the other is large scale structure, like so Galaxy classes. So we don't have that issue.
Are you doing some extra consideration about the potential systematic that each of the Galaxy survey had in each particular region, or
not beyond what the official analysis look at?
Right. So you're using the weights and each of them are included to the regions.
So yeah, so the product, when we produce the map, we follow all the prescription of all the service to do to make sure that we have the weights and everything to account for the systematics. It does the question.
Yes.
Okay, yes.
So regarding her question and regarding what you said about the program, the correlation because they are super. So I don't understand. So they are sources that may be the same in different surveys there, and that's why you are considering them.
Well, it's not only that, not that they are the same source, but if you have you're doing a source from a galaxy, and there's the witnessing effect with the sample of with lensing is going to correlate with your lens sample, basically because it's what is producing the distortion of the say.
Yeah.
In that sense. But there are no galaxies involved. But I didn't say that much. We didn't say that much, but there's in DS not for sure because they did that for us. In kids and the city are truly different galaxies, so I don't think so.
The correlation in the signal I understand,
Yeah.
that's the observable, but I thought you said the covariance, the cross.
Yeah, in the sense that if you have like different tomography beams, you have an angular power spectra for each of the tomography beams,
Yes.
and they will correlate between them, right? It's not that you have a diagonal error because you will also have like
Because it's
because they have the tails are overlapping and because maybe because of that. Yeah. Maybe because of that.
You're saying EGOS and DPELs don't have this, no share TV at all? Yeah.
No, because they are very different perceived. So basically, these are pressure distributions, these are kernels, and you can see EGOS here, the overlap with DPELs is so the equations are basically this one. And DPELs are basically these ones. And there is no other one. And also we are not accounting for any cross correlation between clustering flows for the reason that Anna said that you have to be very conscious that your calculation might be wrong.
So DLS is DPELs?
Yes.
Okay.
We changed it because of some weird reason that I don't remember.
But between kids and pickups, there could be shared galaxies.
But
You can
one
be-
is used for shear, one's used for.
Exactly.
Yes.
Yeah, they could be that they are using.
But yeah, that's a weird.
Yeah, we have. Yeah.
So we, with all this data, basically we are coming all the way up to redshift 2, where the quasars are basically at high redshift. And interestingly, basically you can see that the range of redshift that we are probing with both subdivisions are basically the same between 0 and 1. So the idea now is that we can do tomography with 3 times 1 when we want to do the reconstruction of the growth. This is basically when you do the cross correlation of galaxy clustering and cosmic shear, you are doing the integral that I showed you before with a kernel that is very narrow and something that is broad. So approximately, this is proportional to the sigma 8 or the amplitude of fluctuation at a specific time of your galaxy sample times the bias. So if you account for the other terms, like the autocorrelation of galaxy clustering, you are able to break the degeneracy and actually measure sigma 8 as a function of redshift. So this is what we did. We have here S8 on the vertical axis, redshift on the horizontal axis. Let's focus first on the top. Basically, we reconstructed assuming lambda CDM in the background, and we feed the linear growth. In orange, you have the subset that is basically DS. In purple, you have the one that is kids, and the combination of all is in red, and the prediction from Planck is in blue. And you can see that these data sets agreed, which is now known because many people have checked the agreement between DS and kids in the same footing, sorry. And you can see that they both prefer this lower value of S8 at every time. So basically, the tension that we were seeing today were actually driven by this under prediction and perceived 0.3. And if you want to understand what was driving this tension, what we did is basically we take the full sample and then we remove cosmic shear from it. So we have only galaxy clustering and cosmic and CMB lensing. In this case, you have something that is compatible with predictions and in lambda CDM. Yes.
So the tension that you would see in the Redshift zero kind of plot would be like if you integrate along the planned, like lambda CDM line.
It will be like if your data is actually fitting this. I mean, just lambda CDM. So you have coming like this blue, and then it will fit this, and then you will have.
Okay.
And yeah, so basically the tension was basically driven by SEER in at least in this data set.
Sorry, Carlos,
Yes.
another thing is this. The blue line is the prediction from blank primary anisotropies.
Yes.
Okay, and when does like see evidence gets in?
Simulation is used in with the in SD and FE and FT and in all the large scale structure. But really it only plays some role when you remove SEER, because SEER is outweighs CMB lensing. So it really does matter when you have galaxy clustering and CMB lensing.
And you do all the cross correlations.
Yeah, exactly.
Like it's assuming lambda CDM, I guess.
Yeah. And then, because we had to test that our pipeline was robust and everything, we did many tests in lambda CDM to see that we recovered the official results. Here I'm showing the results of sigma 8 omega matter in lambda CDM, DS constraints in orange, the kids cross DESI in purple, and the combination of everything in red and Planck in blue. We found really that we saw that they are actually in perfect agreement when they are analyzing the same footprint, in the footing. That we found a really NSA value that has almost 1% errors, which is kind of what you will obtain, I think, with LST GR1 or something like that. So pretty small errors. And just to put it in context, and so a little bit, this is in this plot that we saw before. The tiny plot point there is the one with our measurement. And this is just to highlight that we should aim to do combined analysis in the future. Right? It's fine to do just one of the survey, but we should try to aim to try to combine them together to really extract all the information we can out of it. This is a lot of work, and it's understandable that each collaboration focus on their own data, but just to have in mind that we can really push down the error bars if we do these combined combinations. And something just more recent, like something that I worked with Mateo Senaro, Giovanni Rico, Raul, and Angulo, and David Alonso. And it was out this year in March, just again 1 week before the DESI results. So maybe many of you missed it. So basically, what we did is basically combine DS and KIDS, DS-Y3, KIDS 1000, and HSC, and going to very small scales using the backbone emulator that Mateo explained before. And just to have an idea of what I mean by small scales, this is a plot taken from Cyril Do's paper in the official analysis in harmonic space of DS-Y3. Here is the relative difference between on the angular power spectra between a fiducial model and some modeling choices changes as a function of multiple error. The gray band shows the fiducial scale cuts, and basically you can see that you can have suppressions up to L100 almost with illustris. So the scale cuts typically nowadays, just to be very conservative, are of order 100. But we wanted to go to much smaller scales. We went to 4,500 in the fiducial analysis and even 8,000 in the more drastic case. So following what these DS and KIDS did, and also what Emily Longley did before, basically we removed the overlapping area so that we have to model the covariance between the different angular power spectra. This is without losing almost any signal to noise. So we just saved a lot of time and we lost very little. The only question was that what happened with the DS and HSC, that they both use the same samples to calibrate the Rossi distributions. So there would be some spurious correlation because of that. Fortunately, this is something I worked on like a year before, like in the combination of DS and HSC. In this case, DSR1 and DSR6. In this case, there is no overlap, so there should be no correlation at all. However, because they were trained with the same Rossi distribution, you can actually find correlation on the Rossi distribution. sorry, it was trained with the same training sample, there are correlations on the residue distribution. To account for it, basically we recalibrated DS residue distribution with Cosmo using a TIR method as in kids, sorry, in HSC. So, and then we estimated the covariance. And you can see that this is for one tomography beam of DS, and this is for one tomography beam of HSC. And if there were no correlations, this will be 0. However, you see that they are here. So actually, having used the same training sample and the calibration of the residue distributions, introduce a correlation among them. And you have to propagate, you can propagate this to the angular power spectrum. And you can see that there are off-diagonal terms that match. This is DS covariance, this is HSC covariance, and these diagonal terms that appear just because you have correlations on the residue distribution. So potentially that would matter. However, fortunately, this does not. This is not the case when you do the inference. So here it is the analysis within lambda CDM, SA to megamatter, HSC in red, DS in orange, the combination in yellow, and the line is the combination without accounting for these correlations. And you see that you obtain exactly the same. So the question now is, what will happen in the future with NSST and EP?
One question. Did you assess the consistency between HSC and DES? You can combine them.
Like I said, that was not the question that we want to answer in the paper. And yeah, it's like this is like 2 and I don't remember the name, the number, but it's 2.5, 6, something like that. Yeah. If we wanted to, if the important thing was reporting a safe, it would be important, but because we just wanted to know if it mattered, if the correlation mattered or not. It was not that important, but yeah, it's borderline.
I think I missed how. So there, like, what is the element that you use to? Maybe it's okay. So you're using DIR for both.
Yeah.
And then deciding, but then in the end, DS didn't use DIR. So what is?
No, it's exactly not we use DIR because that's what HSC did, and that way it was easier. That we just had to recalibrate one, and by using the same method, we could easily compute this.
Yeah.
The question, the important is not the method that you use. That's what simplify your life to do the analysis. Or the important is that they used the same example.
Right.
So
I guess like questions like now, if I give you DS and kids and HSC as is, do I know how much correlation there is?
by hand, but just by giving that information, no. You need to do.
To make these simulations, but don't you need to simulate
This
the
is the
process?
simulation. This is actual data. This is the.
Exactly, but do you need to simulate the process they make the redshifts?
No, what we did is we recalibrated with we calibrate both at the same time. That allows you to have an estimate of the variance. I don't remember exactly the details. We can review that later. And then it allows you to give an estimation of the covariance, basically, by doing it at the same time. I think maybe at least for the arm that was the key part that you need to do simultaneously. Not just without evidence will be different.
You'll need to redo the redshift too.
Yeah. But as I know here, it should not be it should not be a problem. In theory, this is the worst case scenario. We do have like just at any passing Cosmos served by these two services. In the future, it should matter less because we have a larger footprint and everything. So our takeaway is that probably it's not going to be important. Although maybe it's good to reach it. So going back here, by having this the data and removing the area is enough to not worry about the correlations. Also because you checked that with simulations that they were not the correlations. So that also simplifies my life. So in the residue distribution, you have the DS in the top, kids in yellow, HSC, and then the kernels on the bottom. You can see that HSC is the one that goes to higher residue. They have signal almost all the way up to 1.25, which means that it's going to be, in theory, more sensitive to smaller scales. And it's interesting that DS and kids, if you look at the kernels, they look pretty similar. They are, it looks like they were designed like that. Not sure if that's the case, but no. Okay. And then, well, I just quickly, we use the Baco emulator to be able to go to these smaller scales. And I will just show you this parameter. All the other stuff, Mateo explained it. This is the only parameter that we are sensitive to, MC. That is the characteristic halo mass at which half of the gas have been expelled out your halos. And the larger MC, the larger the suppression. So basically, you can have suppression up to 30%, so pretty big suppressions. Sorry, I'm plotting here the suppression that you can get on the matter power spectrum when you account for baryon effects as a function of scale. So going to the results, the fiducial analysis, we need up to L4000 because the official analysis of TS goes to 2.5 arc-minutes, and I think by reading the PSF paper below 2.5 arc-minutes, there were some PSF thinking. That was a reason to cut it there. Okay. Oh, that's what I understood.
I also saw that in the paper.
Yeah, yeah.
Especially that way.
No, it's not. I think it's fine. I think that below 2.5 arc-minutes, the problem is that you start seeing effects of the camera because it's below there. So I think that was the issue. So we cut here just to be consistent with the scales as in DS. So basically, once you put them in the same framework, you have S8 omega matter, you have HSC, DS, and KITS. You see that they all agree pretty well, and you have the combination in solid contour. You see that you don't get that much in the S8, just like a little bit respect to DS, but your major gains are on omega matter. You have a pretty tight constraint omega matter and pretty low value in omega matter.
So do you have a comparison with the CDU paper?
With which one?
The CDU paper.
The CDU, which is the
With L equals to 400 or something.
No, sí,
No.
sí, yes, at the end of, yes.
Sorry to.
Yeah, but it's applying the same scale gas as in, more or less the same scale gas as in CDU paper. So the official analysis result is in black.
Right.
The one where we don't account for variance but use Baco emulator that is similar to asymptotic precision. So is the solid line, and using halo fit is the dashed line. The scale gas are not exactly the same because the meaning is not exactly the same because we use a higher resolution and there are something.
No, but I was asking to compare
The size of the
with the L up to 4,000.
I have it in the paper. I don't have it in the talk.
Okay. But you shrink a lot?
No.
No.
I was.
And that's what Mateo showed, right?
Yeah. I have actually yeah, I can show it now and then I show it later. So jumping to this part.
Sorry.
That's fine. The issue now is that we are dominated by systematic effects. So this could be similar to what Cyril used. It's a bit more dramatic, but it doesn't change that much. But if once you account for baryonic effects and you marginalize over them, you are dominated by the uncertainty in them. And you can just go to whatever scale and you will not find. This is for the combination of all of them. I don't have in the slides just for DS. But the story is slightly different in the sense that DS is not that sensitive to baryonic effects. It's the difference between the solid and the line is not that dramatic. So even if you ignore baryons at L1000, even L2000, you are not too bad. I have the plot in the paper. Hasta. How can I? How can I make it bigger? Okay. Oops. So if you look at the constraints that you get from the variance suppression from weak lensing, you see that the data weak lensing alone is not very sensitive to at this moment is not very sensitive to baryonic effects. That is because the signal to noise is saturated about L2000, and we find if you compare it with the hydro simulations, you find something that we are preferring the weaker one. So here We have eagle on the top that is pretty weak baryon effect. Then you have Illustris TNG, that is kind of good agreement, Bahamas, again, Bahamas, owls. The one that is a bit more in disagreement is Illustris, but again, that's 1 sigma, so you will be in the regime of 3 sigma agreement or disagreement with Illustris. So this cannot be taken away. But if you remember the plot that Matteo showed before, Giovanni found when he did the analysis of DSY3 in real space with baryon effects, he found a stronger suppression. And the reason that the way we convince ourselves that this is correct, apart from doing many tests, is that real space statistics, correlation functions, are actually more sensitive to smaller scales than Fourier space. And this is because when you want to go to correlation function, you have to do an integral of a Bessel function that has support all the way to infinity of the CL. And then in the end, you are taking more information out of the non-linearities. That's our interpretation.
Do you have an idea, or I guess, of why the shape of the suppression goes up?
Yeah, well, this is because there are many models that maybe the suppression is like this. This is one, and then you do like this, and then just follow that. Like maybe you're entering the halo galaxy.
But in this case, where you are in, like this is with the baronification signal.
Yes.
In that case, MC only.
No, we're running everything. I just saw MC because it's the only we are sensitive to.
That's something like M1s and
Yeah.
Okay.
Yeah, the 7 parameters are varied in all these results.
But then it's nice, and it's that relates physically, no, to like some impact on the galaxy, like the very inner.
Yeah.
Part.
Yeah, that's I think that's the reason why it goes up. Yeah. So if we compare it with what will happen if we ignore baryons, in the case when we have combined the 3 surveys, what we see is that we will have an overpredicted or constrained S8, about a 30% over constraint. By marginalizing our uncertainty on baryonic physics, we reduce the tension from 2 point something to 1.8, which in my opinion is not really tension anymore. And then the problem is that because we have increased the constraining power a lot in omega matter, we have a new tension in Cosmology that is going to be this time on omega matter, 3.5 sigma tension. We did many tests just to make sure that this was not an error, and we could not find anything that could cause it directly. Doing a suspicious test that takes into account the whole posterior distribution, we reported in the paper tension between 2 and 3 sigma. The interesting thing about this new tension is that it can be recasted onto a H-law tension. So if you remember the Ariel Sanchez paper from 2020 that he proposed to remove H's out of observational cosmology, I'm pretty much in favor of that. If you have S8 has sigma 8, and this 8 has Ulyss. Is your variance on your field in a sphere of radius 8 megaparsecs over H. When you're doing CMB analysis, that's fine because H is pretty well constrained. H is 0.67 plus minus 1%, more or less. However, in weak length analysis, this is not true. You are prior dominated. You are not able to constrain H, at least nowadays. So it really, the variance that you're looking at is in a sphere of radius that goes from 9 megaparsecs to 60 megaparsecs. So from there, it could make sense that you have different results, at least in my naive understanding. And here, if you go to this new parameterization that he proposed, the S12, where you have replaced sigma 8 by this sigma 12 and large omega by little omega. Little omega is large omega times H squared versus omega matter, little omega matter. You find no tension, no tension with Planck. So you have the fiducial results in the solid contour and Planck in black. The tension goes away. However, this is like, okay, if the problem is that we are not constraining H, what happens if we impose a prior on H? And what happens if we put a prior that comes from supernovae, from Riess value of the supernovae? That's the blue line. Then still there's no tension. And what if we put the prior that comes from CMB, from Planck? Then again, you have the line, the yellow contour. Again, you have about 3 sigma tension. So this is interesting that this can be also recasted on that H no tension. in order to continue investigating a little bit more the nature of this tension in omega matter, what we said is, okay, instead of putting a prior, let's add some information about the background evolution that comes from PEO, like PEO distances. This is from SDSF because, as I said, this is a week before the sleep results. When you introduce the PEO prior, you have the green line. You see that the contour has moved quite dramatically to the larger values of omega matter. However, the tension is reduced to 2.8 sigma, but your chi-square, your fit to the weak cleansing data is basically the same. The number, I think, didn't change at all. So this is interesting. This is interesting that just by introducing something that constrains, that moves this much, your posterior does not affect your fit to the data. Could be that this is a prior volume effect. It's something that it will be interesting to keep investigating.
Have you tried with a prior NS?
NS, no.
Because, yeah, because it's also not well constrained. I mean, it's something that in Euclid, they try also to apply. I don't know. Very, yeah. DAO must be helping on some of these parameters. I get it's not or something else.
Okay, I can think of fixing the NS. So,
What's your prior?
it's broad, but I don't remember. It was compatible with Planck, but pretty broad. And then whatever this DS was using, I don't remember the numbers. Yeah.
It's pretty broad.
So, yeah, like most of the analysis is following DS. So yeah, I don't remember, but pretty broad. So just going to the end of my talk, I think on time. I showed you already this. The problem that we are facing now in cosmology, at least in large-scale structural data, is that we are being dominated by the systematic effects, in this context, the variant suppression that we don't know. As I mentioned before, the constraints with if you ignore variance solid contour, if you account for, if you marginalize over baryonic effects, is the line. It doesn't matter what scales you use, you are completely dominated by your uncertainty and baryonic effects. And this motivates, and what happens if you introduce a prior on the BCM parameters? In this case, I took a prior from Bahamas. Not that this is right. This is an example. You will really increase the constraining power in S8 by about 30%. So this motivates to the discussion of this afternoon, that basically is what happens if you actually do an analysis that constrains baryonic physics by using tracers of gas, tracers that really are sensitive to the astrophysical processes. And this is something that I work with Tasha Ferreira and Newton Fell in Oxford. We use the cross-correlation of TS-Y3 with cleansing with the diffuse background of X-rays from Rosat. And you can see here on the right, the constraints on the parameter I was showing before, MC, that is basically the strength of baryon suppression. The constraint that we got from with cleansing, and the constraint that she found with just one survey and X-rays, a pretty tighter constraint. So this really highlights the need of trying to model the problem. The caveat with this analysis is that the cosmology is fixed because we don't have a model that allows us to constrain cosmology and calibrate systematic effect, the baryonic effects at the same time. So that's the to-do thing. But it really highlights that you can increase a lot the constraining power. And just a slide that I put just before the talk, this is something I'm doing also with Adrian Laposta in Oxford. That is not only using the DS, the X-rays, it's also adding the cross-correlation with TSZ and with cleansing from TS-Y3. I'm sorry for changing the suppression, but I didn't have other product. I took it from the draft. And you can compare it really with what we were seeing before in the talk with cleansing only. And you really are able to ping down this. There are caveats to this analysis, but I will not enter into details now. We can discuss it later on the discussion. So really, I think that yes.
So here, are you still using 2015 for the DSC data?
I need to check the drafts. I think it's 2018. 18. Yeah.
This is the Rosat footprint, and this is the best footprint.
And TSZ is total because I have all the plots. So there is,
You're doing cross correlation, but they don't match, they don't overlap. They don't understand.
yeah, they are observation, no? They are like.
The blue is the rose. The gray is the mask.
The array and the mask.
Yeah, sorry, yes, what you want to say is the great thing. Yes, yes, so,
This.
okay, sorry, okay.
Sorry.
Okay, I would say that I
Yeah.
would color code the name of the design. Okay. Okay, no, that's fine, sorry. Okay. So, yes, just to finish here, if we want robust constraint cosmology, we need robust and fast data analysis methods that are available at the moment, and we need data from many different rows so that we can test our modeling and calibrate systematics. And very soon, hopefully, Cosmotica will be available for everyone to use. And I will leave here my three main money plots of the problem. Thank you.
So your last result and which we're going to constrain MC, how does it compare with other Hilo simulations? I mean,
You mean in the TSL one? This one?
no, the one in the summary, like this right, the right, sort of right plot.
That's right.
Yeah, that's.
So,
When you constrain.
yeah, the boost, you mean the SK, the constraint?
Yeah, but this suppression, how.
Is in agreement with what Giovanni found, and is in between. If you remember the paper from Amon Estasio for DS and for kids, that one is like lower, and the kids is lower, and the DS like higher. It's kind of between. Basically. Yeah, yeah. I don't have the plot, but it's kind of like that.
So yeah, the last abstract thing, so that's also in the verification framework.
Yeah, but in Halo model. So it's a Halo model that we account is the VCM model, but in the Halo version. Halo model, not in the embody thing.
It's not HM code.
Not the same code. It's inspired in HM code. I think actually the modeling is similar to HM code, but we put all stuff there.
But do you have additional parameters to model X-ray and TSC?
Yes, so you have the MC, you have also at some point you have to relate your pressure and your density, and you do it with a polytropic, with an exponent that is basically called the polytropic tab. You have those two, and there are another two, I don't remember at the moment. But yeah, it's a parameter that are specific for this. And you think that some of them are shared with the TSF, but they have a different dependence on the, I think, if I remember correctly, on the density, and they can break the generosity.
So that's quite a big change.
Just
like how tight it is.
Yeah, well, but it's because we mentioned it currently is not that sensitive. I have, the thing is I don't have the plots for, yeah, just like to get, I mean, if we go back to the,
I guess like, do we
I
actually
mean,
think that?
this is what you get from
Yeah.
the Wickland, so it's not very,
Yeah, so you're saying, but you believe that we actually know MC to that level?
no.
Okay, cool.
No, the thing is that, I mean, the model relies on use a fixed cosmology, which that might affect things.
Cosmology is fixed.
See, fix the model is kind of simple, so there are, ideally, I would like Mateo to come up with another X-ray prescription, say later, and do that. So, so there are some limitations with the model in the, and
So which attention metric do you use when you report the attention?
so for when I was in the 2 sigma tension, sigma tension, it was basically assuming they are Gaussian distributed and just one. For the overall tension that I was reporting is suspiciousness, that is, in theory, accounts for the whole probability distribution of the posterior, and suspiciousness. I think it's this paper from Will Hanley, Pablo Lemos, and other people. I can send you the reference and there.
I don't make sense in when you show the sigma one and of the other experiments.
You what?
One had a really tiny error
Ah.
bar, right?
Yeah.
But I didn't know the dependence on the how confident.
It's a very good question. So I don't have the plot here to show you, but because as I said, weak lensing data is not that sensitive to variability effects, although we might be very worried. In DSY3, in KIDS 1000, you can go to L2000 and you don't see anything. And KISS 1000, if I remember correctly, was more constraining than DS with cleansing in that time, in the FTR1 with cleansing. So if you can go that with KISS 1000, I would expect that it's safe also to do it with DS1. So fortunately, that was the result, and now I'm much more confident that I'm confident. I can show you the plot later, but it's really for the individual service, you don't see that much effect on marginalizing or non-marginalizing other coding effects.
I don't remember right now. I don't remember right now the value for the BAO from BS. How much is the actual with this one about
The value of
BS Y6? Like there was in some of the talks these days. I don't remember.
So I showed the result, but I didn't show the constraint on omega m because they use the preparing preparation. So it was only like the angular PAO measurement. It's into sigma with Planck. But then I can below Planck, but when you run a cosmology chain, it won't be to sigma tension because it's just 1 point.
Yes.
And I can advance that it just in lambda CDM because Planck is super constraining. This only video measurements just shifts slightly the constraints from Planck. And it's not intention because you just consider that single point these are very broad constraints. But we are looking at the impact on extended models like W, not WA.
It was still consistent with the measurements by the actual measurements by the right?
It was consistent with this that is also a bit low our advanced redshift range. So yeah.
And the C, I don't remember which is the megawatt and the C is for.
I think all of them are slightly lower than Planck, slightly, but compatible. The only one that is in disagreement with Planck, apart from this result, is supernovae. That's interesting.
Exactly.
It's like
that when you combine with supernovae, which is into sigma, we find that everything is intentional.
Yeah.
And we find the same thing when we combine the SPAO with the supernovae is similar to the GPAO and the supernovae.
So in that line, just because I don't know really about that, it's supernovae from RESOR, there's like several different kind of surveys for supernovae that potentially have different systematics there.
So in the resi paper, they use 3 different sets of supernovae, and with all of them, they have this text being WA. But
it's supernovae, but I don't think it's the calibration of the supernovae. So you are not sensitive to it. It's just the light curves. So you are sensitive to the expansion rate. But in BS Y5 supernovae, they find omega matter 2 sigma high.
exactly. Yeah.
It's like fighting attention without.
Yes, interesting, and we are still gathering, computing on the attention metric for this video of supernovae.
I mean, maybe it's remembering like checking the wrong paper right now, and like it says that Pantheon plus like omega matter of 0.33, which would be consistent with Planck over there in that plot. Right?
Yeah. Okay, thank you. I think we could combine to like the schedule.